Electric motors provide the mechanical energy that's needed to operate a wide variety of equipment in industrial facilities. For example, pumps, agitators, fans, compressors, and motor-operated actuators typically depend on electric motors to function. An electric motor is a device that converts electrical energy into mechanical energy. This mechanical energy is in the form of a turning motion. The turning motion can be used to drive a load that is coupled to the motor. The turning motion is produced by the interaction of magnetic fields that are created in the motor. In fact, the movement of an object, such as the rotating part of a motor, as a result of the interaction between magnetic fields, is called motor action. To understand how electric motors operate, it's helpful to start with a simple example of how a magnetic field can be created. This illustration represents a section of wire with current flowing through it from negative to positive. The flow of current through the wire produces a magnetic field around the wire. The magnetic field consists of a series of lines known as magnetic lines of flux. All motors work because of the interaction of two or more separate magnetic fields. The interaction between the magnetic fields can be used to create rotary motion in a motor. We can use an illustration to see how this is done. In this illustration, a loop of wire is positioned in the magnetic field created by two permanent magnets. The loop is connected to a source of direct current, or DC power, which is not shown. Current flows from the negative side of the DC power source through the loop to the positive side. The current flow produces magnetic lines of flux that are perpendicular to the loop. As a result of the magnetic field around the loop, magnetic poles are created. In this case, the poles are perpendicular to the loop. The North Pole is here, and the South Pole is here. In order to show how the magnetic field around the loop interacts with the magnetic field of the permanent magnets, we'll represent the poles created by the loop with a simple bar magnet. The bar magnet is pivoted so that it is free to rotate. Now we can see that there is a pair of each type of magnetic pole in this situation. There are two north poles, which are next to each other, and two south poles, which are also next to each other. Like poles repel each other, so the interaction of the magnetic fields causes the bar magnet to rotate, and that's an example of motor action. As the bar magnet rotates, the repelling forces decrease because the like poles are getting farther apart. However, unlike poles attract each other. The bar magnet's north pole is attracted to this permanent magnet's south pole, and the bar magnet's south pole is attracted to this permanent magnet's north pole. The attracting forces increase as the unlike poles get closer to each other. So when the unlike magnetic poles are closest to each other, the attracting forces are the greatest. At this point, the bar magnet would stop rotating unless its momentum is great enough to carry it past the poles of the permanent magnet. This example illustrates only part of the rotary motion that's needed for a motor to operate. To keep the bar magnet rotating, the polarity of one of the magnets must be changed. Real motors use magnetic fields that change polarities to produce a continuous rotary motion. The way that this is done depends on the type of motor and whether it operates on alternating current or direct current. However, the basic principles that we've gone over here apply to all motors. A motor works because of the interaction of magnetic fields. In this simplified example, one field is produced by a bar magnet, and a second field is provided by two permanent magnets. The interaction between the two fields produces a turning motion. In other words, they cause the bar magnet to turn. However, the movement of the bar magnet would stop when its south pole is next to this permanent magnet's north pole, and its north pole is next to this permanent magnet's south pole, unless conditions change. One way to continue the bar magnet's rotation is to change the polarity of one set of magnetic poles. In an AC motor, this is accomplished using wires coiled around iron cores to form electromagnets. the electromagnets take the place of the permanent magnets used earlier. To explain how this works, we'll start with a single wire coiled around a single iron core. When current is supplied to the coil, magnetic flux lines are produced. When current flows through a wire that's shaped into a coil, the individual flux lines that are produced join together to create one large magnetic field. The core serves to concentrate this field so that it can have a maximum effect. Current flow through the coil creates a north pole and a south pole. Most AC motors have at least two coils in series. This illustration shows two coils around two iron cores. The two coils are connected in series. Alternating current, or AC, flows through the coils in one direction, and then reverses and flows in the opposite direction. As the direction of current flow alternates, the polarity of the coils changes. The alternating polarity can be used to produce continuous rotary motion in an AC motor. We can see how this works by adding a bar magnet between the two coils in our illustration. The bar magnet is the rotating part of the motor in this example. It's called the rotor. The two coils are the stationary part of the motor, which is known as the stator. Every AC motor, regardless of how it's designed, has a rotor and a stator. The rotor and the stator have magnetic fields that interact to produce continuous rotary motion. The like poles repel each other, so the rotor begins to rotate. The rotor's momentum and the attraction of its poles to the unlike stator poles also contribute to the rotation. As the rotor is turning, the current flow through the coils reverses direction, which causes the poles in the stator to reverse. So once again, the like poles are next to each other. The like poles repel each other, and the rotor continues to turn. As the rotor turns, the current flow reverses direction again, changing the polarities of the stator coils, and the rotor continues to turn. This cycle continually repeats, which results in continuous rotary motion. In this example, the stator has two coils of wire. These coils can also be referred to as poles, since they become north or south poles during normal motor operation. Keep in mind that the example of AC motor operation we've used has been simplified to help make things clear. For example, a motor with multiple poles works in much the same way as a motor with only two poles. Also, the rotor in an AC motor is some form of electromagnet rather than the bar magnet we used in our example. Although AC motors are the most common type of motor used in industry, direct current or DC motors are also used. One common use for a DC motor is as a backup motor for a critical process. DC motors can run on the direct current supplied by a battery when there is a failure in the alternating current supplied to an AC motor. For example, this DC motor is used with a backup pump that supplies oil to the bearings in a large piece of equipment. Normally, an AC motor drives a separate pump that supplies oil to the bearings. But if that motor fails, the DC motor-driven pump can be used to provide the oil. This is an illustration of a DC motor. In this simplified example, the stator consists of two permanent magnets. The rotating part, which is shown as a loop of wire, is called the armature. The armature is connected to a source of DC power. These two components are called brushes. The brushes are connected to a DC power source. A conducting ring, known as a commutator, is mounted on the end of the armature. The commutator is not a solid ring. It consists of conducting segments that are separated from each other. During operation, the commutator makes sliding contact with the brushes. Current flows from the negative side of the DC power source through one brush to a commutator segment. The current then flows through the armature in this direction, back through the other commutator segment to the other brush, and to the positive side of the power source. The poles are perpendicular to the armature. So when current is supplied to the armature, motor action is produced. The interaction between the stator's magnetic field and the armature's magnetic field causes the armature to rotate. Even though the armature has turned, the current still flows from the negative side of the power source through the armature to the positive side of the power source. However, the commutator has physically changed the direction in which the current flows through the armature. This change in direction changes the polarity of the magnetic field created by the armature. So the brushes and the commutator in a DC motor enable the armature to change its magnetic field, and as a result, the armature turns continuously. The example we used to explain the operation of a DC motor was simplified to help make things clear. Both the construction and operation of actual DC motors are more complex. For example, the stator in a DC motor is usually an electromagnet, not a permanent magnet. Well, in this topic, we looked at basic motor theory, and we looked at the fundamentals of both AC motors and DC motors. Now try some practice questions that relate to this material. Now we can see that there is a pair of each type of magnetic pole in this situation. There are two north poles, which are next to each other, and two south poles, which are also next to each other. Like poles repel each other, so the interaction of the magnetic fields causes the bar magnet to rotate, and that's an example of motor action. Alternating current, or AC, flows through the coils in one direction, and then reverses and flows in the opposite direction. So when current is supplied to the armature, motor action is produced. The interaction between the stator's magnetic field and the armature's magnetic field causes the armature to rotate. This is a typical AC motor. Its external parts include a frame, a shroud, and an end bell. The frame houses the stator and the rotor, and it also provides a means to mount the motor to a foundation. This motor is designed to be mounted horizontally. But not all motors are mounted horizontally. In some situations, motors are mounted vertically to drive vertically mounted shafts. For example, these vertically mounted motors drive sump pumps. Motors can also have a variety of frame designs. Open frame motors are commonly used in non-hazardous areas. But some process applications require motors to be completely enclosed. Electrical equipment can cause explosions in areas where there are flammable liquids, gases, or dust. In these areas, totally enclosed, explosion-proof motors are generally used. During normal operation, an AC motor produces heat as a result of current flowing through it. Many motors use fans and ventilation openings to get rid of heat. On this particular motor, the shroud has openings to admit air into the motor to cool it. A fan cools the motor by pulling in air through ventilation openings in the shroud. As air is blown across the motor frame, the air carries away heat produced by the motor. Smaller motors may be cooled by simply letting heat escape from the motor frame. Other designs are also used to remove heat. For example, this motor has a set of fins. The current rating is the amount of current the motor can draw during normal operation without being damaged. The amount of current a motor actually draws usually varies over a range. The amount of current drawn at any one time depends on the load on the motor. In other words, how hard the motor is working. Horsepower is a rating of how much mechanical power the motor can be expected to produce. The operating speed rating refers to how fast the rotor is designed to rotate during normal operation. Most of the information on a motor's nameplate can be used to determine what a motor's normal operating conditions are. This information is important when a motor is selected for a given application. And it may also be important to maintenance personnel. Let's continue now by looking at some of the internal parts of a typical AC motor. This is a stator from an AC motor. The end bells in the rotor have been removed to see the stator better. The stator contains several coils of wire called stator windings that surround the rotor. Current flow through the stator windings produces magnetic fields. The windings have been dipped in an insulating varnish and then baked. The fins provide additional surface area to dissipate heat into the surrounding air. Another important part of a typical AC motor are the end bells. The end bells house the bearings that support the motor's shaft. Bearings provide support for the rotor shaft and allow the rotor to turn. For proper operation, bearings must be kept lubricated. Lubrication reduces friction between the bearings parts. There are some motors that use sealed bearings that do not have to be relubricated for the life of the motor. The bearings of some other motors are greased through grease fittings as part of a regular maintenance schedule. Other motors use a constant level oiler. A constant level oiler holds a small supply of oil that drains by gravity into the bearing. The design of the constant level oiler allows the operator to look at the level in the reservoir and add more oil when necessary. A connection box on this motor protects the motor's wires or leads from damage. These wires electrically connect the motor to a source of AC power. All motors are designed to operate according to certain specifications. Many of these specifications are listed on the motor's nameplate. For example, this nameplate includes information about voltage in volts, current in full load amps or FLA, horsepower designated as HP, and operating speed in revolutions per minute or RPM. The voltage rating that's shown is the motor's normal operating voltage. A motor can be damaged if it is operated for extended periods of time at a voltage other than its rated voltage. The varnish insulates the windings from each other and prevents short circuits or grounds that could damage the windings. The rotor is mounted on a shaft. This rotor is made of conducting bars that are shorted together by end rings. The rotor bars with their end rings are attached to a shaft so that the whole assembly can turn together. As the magnetic fields generated by the stator windings pass through the rotor, a voltage is induced in the rotor. The voltage creates current flow through the rotor, which creates another magnetic field. The interaction of the magnetic fields generated by the rotor and the stator windings produces motor action, which causes the rotor to turn. In this part of the program, we'll look at a disassembled DC motor to identify and discuss its parts. The major parts of this DC motor include the frame used to house the stator and armature, the stator, which you may also hear referred to as the field, the armature, and end bells. The stator is made of coils of wire that are wrapped around iron cores. The coils are electrically connected to a DC power source. The armature contains several loops of wire that are wound back and forth. All of the loops make an electrical connection to the motor's commutator segments. The electrical connections to the commutator segments are protected and held in place under a wrapping of varnish-coated fibers. Current flows from one commutator segment through the armature and back through another commutator segment. The commutator makes sliding contact with a set of brushes. The brushes, which fit in holders, are held against the commutator by springs to maintain contact and to provide a path for current flow from the power source to the commutator. Brushes are a frequent maintenance item for DC motors. Because they rub against the commutator, they wear down, so they must be replaced periodically. Sparking or arcing near the brushes or on the commutator can mean that the brushes need to be replaced, or that they're not making good contact with the commutator. In addition, brushes can chip, which impairs their effectiveness. The commutator should also be checked periodically. Any scoring or grooving on the face of the commutator may indicate a problem. In this topic, we looked at the parts of both AC motors and DC motors, and we discussed their functions. Now try some practice questions that relate to this material. Bearings provide support for the rotor shaft and allow the rotor to turn. The commutator makes sliding contact with a set of brushes. The brushes, which fit in holders, are held against the commutator by springs to maintain contact and to provide a path for current flow from the power source to the commutator.